name is Mohamed-Yassir. I'm a BC student, a NOUR Hassan first Morocco, a NOUR Florent of French. This work is collaboration with Professor Domingo Barrera, Abdullah Lamni, and Ahmed Zidna, which subtitled by a new uniform UE-spline quasi-interpolants and application to isogeometric analysis. The outline chosen for this presentation is as below. So first I will start by introduction, afterward talk about UE-spline basis and new uniform UE quasi-interpolant with Martian identity quasi-interpolant, and afterward we move to application to isogeometric analysis, and we finish with conclusion. Now let's start by introduction, and let's get this example of differential problem, or with for example elliptic problem that is characterized by this equation with L is operator, and we have boundary condition, even Dirichlet or Newman. So as we know, by weak formulation or variational problem, that we can with some condition of A, continuous cursive, and condition with if we can set that the problem has unique equation by using theorem Lax-Milgram theorem. And when we want to approximate solution, as we know, we use Galerkin approach, which means that we choose subspace that's included in the real space with that contain the real function, and we try to approximate solution by using this equation. So in general, we found a linear system like that, and by inverting this system we found the solution. Okay, but in general we choose finite element method, okay, which use approximation of polygonal partition by triangular mesh, and that is not good because the lack and for exact geometric representation, for example, usually polynomial curve and conical section. Also, the approximation is always depend to size of mesh, and that's make refinement iteration require an interaction with the geometry. So, but in the AGA or isogeometric analysis, yeah, sure, it's also used like finite element isoparametric approach, which is mean approximation of the physical domain and this by function, but it chooses a domain like that which is square and starting to approximate each by geometric function, which is like that. And the function that we can found at last is the basis with the reverse of geometry, which is writing like that. So the EGA is normal used by using the nervous, by using tensor product and for, but it is not in general good because we have problem to approximate some shape like conic, like trigonometric function like that. So we try to change this idea by using a new or a quasi-interpolant. So our objective of this presentation is try to using quasi-interpolant for in place or in terms of nerves and apply it to isogeometric analysis. Now let's move to the other section, which is the UE-spline basis. The UE-spline basis is defined for like that for the order 2 is by this formula, and for order greater or equal 3 is by this, which for order 2 is writing which the omega is like that, and the notch are not uniform with the space and general that. This spline has many properties. For example, partition of unity, positivity, local support, linear independent, differential and derivatives. And as example, for omega chosen uniformly, we found that the UE-spline of degree 3 is writing like that, with A, B, C are as follow. And as example of illustration of these bases, you can find for the notch are chosen like that, and the omega is only 1. Now let's move into our non-uniform quasi-interpolants, and let's start by Mersenne identity. The Mersenne identity, we found that the one equal like that, the cosinus can write in terms of our of UE-spline with gamma and delta as follows. The same thing for the sinus. Afterward, we express the exponential in terms of line, the cosinus power m, and the sinus power n. And the definition of quasi-interpolant is like that, with lambda is the DL function and is writing by this formula. So the alpha and alpha 2, 3 are as follow. And to study the error, we defined this 2, 3 operator that's already presented in the Larry Schumacher book, and we defined the operator, the linear operator that's null our space by that, and we found theoretically that the difference error between the function and our quasi-interpolant is like this. So now let's move to application to isometric analysis, and for as application we take the possible problem, and we choose our basis is tensor product of the 2B spline with the boundary condition, and we choose as example 3 types of solution. So the first type is the direct problem to data, and the other 2 types of solution by quasi-interpolant with using SQP, which SQP is the aversion of all points divided by p minus 1. It is already presented in the RUEL. So as just example, which is for the first times the omega like that with the solution function, and we found this solution. We always found that the type 3, it means the quasi-interpolant with not choosing averaging of all notch is good. So the same thing for the second test, we found the same thing. And now we go to the conclusion that we can found that the UE-spline is valid in the trigonometric and basis and hyperbolic function. Thus, as we found that as we see by Marston is identity reproduce exactly the conic section and all interesting engineering application, not like nervous. And we use it that for construction quasi-interpolants for solving differential problem with direct boundary condition. And as we can show that is give good numerical solution. And thank you for your